All right, Calc 3, welcome in. It's Tuesday, November 23rd, and it's the day before break. And after tonight, man, we only have two videos left. Wow. And that's probably good because we're starting our last chapter of calculus, right? Chapter 15 starting tonight. And so we're going to see a little bit about what chapter 15 is. We're not getting through the entire chapter. That's never been on the syllabus. We end around 15.4, and we don't even get through 15.4 all the way either, right? So, yeah, we'll be finishing this up. It's about a half worth of chapter, and so tonight we'll get to 15.1 and see how that goes. So, chapter 15 is a branch of calculus called vector calculus. Chapter 15 is in general called vector calculus. And as the name suggests, it's calculus, but done on vectors, right? And so we've already obviously had vectors in some capacity up to now, so that vectors are certainly not new. And in fact, the concept we're going to define right now, called a vector field, is not new either. And so let's get started here with the idea of a vector field, right? So a vector field is just simply a function whose output is a vector, right? So it's a function whose output is a vector. And so specifically what we can say is it assigns a point to a vector. So the input would be something like x, y. We would input a dot, a point, a location in 2 space, and we would map it through some function. Let's call it capital F with a vector hat like on it, like that. And it would get mapped to some vector, f of xy, right? And so it would get mapped via that rule. So basically, a point is in the domain, right? And at that point, I think of it being assigned an arrow, a vector. And that's really the idea, whether it's 2-dimensional or 3-dimensional, right? So at every location in this space, maybe I can think there exists a vector according to some rule, right? Now, we have already had some examples of vector fields. The gradient is an example. Gradient of f is an example of a vector field. So for instance, if I had little f is not a vector field, but if I was to start with this little f function like this, I can create the gradient pretty easily, right? Going back a chapter or two, right? I could say, what's the gradient of this? Well, that is going to be the partial derivative of this with respect to x, which is 2xy plus 3y cubed, I, plus the derivative of this with respect to y, which would be x squared plus 9xy squared, j. This would be a vector field, right? Because notice what happens here. It assigns to every coordinate xy a vector. You see that? And so the gradient is an example of the vector field. By the way, little f associated with this is also called a scalar field, to sort of distinguish between the two. And it all depends on, notice that at each point, this gets assigned a value. At each point, this gets assigned a vector. That's the difference between a scalar field and a vector field, okay? And at its core, that is basically it, right? Now, I mean, you can get into fun things like if this field represents velocity, then you have a velocity field. If these vectors represent accelerations, then you have an acceleration field. If these represent forces, then you literally have a force field, right? And that's not even a joke. You have a force field, right? And so basically think of a field as a collection of arrows and vectors, right? Now, as you can see, that this might really model flow of things very well. It'll capture something like motion, right? Like, you can say, like, if I want to observe how water spins, right? If it spins, yeah, I can think about that motion of that system using a vector field, right? And in fact, let me show you some pictures here in the book of some vector fields and their use. Right? You might have something like a rotating wheel. At each location is a velocity vector. If you look at this, if you take a close look at this here, you notice that the vector here in the inside near the center, they are small magnitude. But as you go further down the radius here, near the edge of this circle, see the velocity is faster. Right, and you've probably experienced this, obviously, if you've been on a merry-go-round, right? If you want the fastest ride, you want to sit near the outside of the merry-go-round, and if you want the slow ride, right, the baby seats are here in the center, and they go the slowest, right? And so that's what you have, and you can represent that motion really nicely with a velocity field. You can't obviously see all of the points in a velocity field, but you can certainly graph representatives from that to see and get a sense of this rotation here in this field, right? Here's an airflow vector field, right? You can say that to every location here, I'm assigning a certain flow of air. And so you can see here how that's affected by hitting up against this car, the exact flow pattern that you get, right? That is an example of a vector field. You can get a gravitational field, right? Here is the source or the center of gravity, if you will, and you can imagine that the gravitational force is stronger as you get closer to the center, right? And in fact, many physicists and things, we call this an inverse square field. And here you have the central force field and gravitational fields defined by Newton's law of gravitation, which maybe you've seen this in a physics class before. But this is now talk about in a vector field sort of way, right? You can talk about how that gravitational field looks like, right? And as you go out further and further, this dies down like the square of the distance that you're apart from the center of the gravitational field. Okay, so you can see that there's going to be really, really nice applications of these vector fields. And so it's going to be nice to be able to do some basic calculus with them, right? Because obviously in calculus, we're interested in how things change, what they look like, how can I model certain things, and basically what is the change, right? Is there an idea of a derivative? Is there an idea of an integral? What sort of ideas do we have now applied to vector things, vector fields, right? Now, before we get into that nitty-gritty, let's go ahead and at least just talk a little bit about how would I plot such a vector field? Well, this is actually not a very easy question because we certainly have computers to help us out with this. But you should be able to do like one of these by hand, just like one in your life, just to say that you've done it, right? But then obviously I'll show you some GeoGebra stuff that you can do, and any computer programming in mathematics would be able to graph some vector fields. So anyway, here we go. Let's say that f of xy is negative yi plus xj. I mean, at the start of this, all you would have to do is make a table, right? Pick your x and your y coordinate, plug it in, and see what your vector is, and then plot that, right? So you literally might make a table like you were just starting out learning how to graph functions in Calc 1, right? Like way back in the day, yeah? Right, so maybe I pick, the origin. If x is 0 and y is 0, I pick the origin. Well, I'm talking about the 0i plus 0 vector, yeah? So I'm talking about the 0 vector. So I can draw the 0 vector at the origin. So if I was to start to plot this, I would just have a dot representing the 0 vector there. Then maybe I go out to 1, 0, and I go ahead and I graph that. Well, what vector am I talking about? If x is 1 and y is 0, I plug it in. The 0 wipes out the I component, and the 1 goes in front of the j. So I'm talking about j. So what you can do to represent this is at the point 1, 0, which is here, go ahead and draw the vector j, which is a vector of 1 unit pointing straight up, like that. See that? And that would be the vector represented at the point 1, 0. And then maybe I can do something like 0, 1. And I pick several representative points and I do this. So now plugging in that, that's going to wipe out the j component. Plugging in the 1 here, I get negative I. And so that means at this location, I have negative I, like that, right? And so on and so on. So I could even do something like any of these. I can keep going, picking all sorts of x, y values, and I would end up with something that looked like this, right? Just a few representatives like this. And once I get a few representatives, I can start to see that I do seem to sense a rotation is occurring here, right? A swirling, right? Now, what's with these circles here? The circles are not part of this vector field, but they are drawn here to help you see the relationship between these arrows, yeah? And so let me show you how you might do that. Because you're going to get real tired of just randomly picking points and then plugging in and drawing vectors. It's not going to get you a very comprehensive picture. Now, of course, this is how technology does it. They just literally, hundreds of points, plug it in, and then draw it, and you can see what that vector field looks like, right? But if you're doing it by hand, you're going to get tired of picking dots and then drawing vectors very quickly. So you might want to start thinking of other ways you can think about the qualitative, if you will, not the quantitative, but the qualitative information about this graph. For instance, right, I might ask, well, okay, this is a vector. Have you considered what the magnitude of this vector is? And maybe explore that a little bit, right? Since this is a vector, it has magnitude and it has direction, right? And so I might, if I'm trying to understand this vector field, try to understand the magnitude of the vectors involved. Well, let's go ahead and calculate that. That's going to be the sum of the square of the components, the square root of that. So I'm going to get that. I'm going to get negative y squared plus x squared. And so, of course, that's going to be square root of x squared plus y squared, right? That's the magnitude of all of my force vectors here, or my field vectors, yeah? Now, let's say that this was some constant, and so I set it equal to some c. Well, do you notice that if I want the magnitude of the field to be constant, then this is going to look like circles. Do you see that? And so if I want the constant magnitude to be 1, well, that's going to happen when this is x squared plus y squared equals 1. So that unit circle, all of the vectors that live on the unit circle are length 1. If I wanted length 2, right? Length 2, that's going to live on the circle, all the points where x squared plus y squared equals 2 squared, or 4. So that's why they're drawing the circles there. It's emphasizing a qualitative idea of this, saying any vector that lives on here is unit length. Any vector on here is 2 units long. Any vector here is 3 units long, and so on, right? And so when you start to graph these, you might want to explore some qualitative information by looking at the magnitude, right? Now, with that being said, of course, you can have GeoGebra help you out with graphing this, yeah? And so let's take a look. I uploaded a couple different vector field GeoGebra programs for you to download. And so I did not create either one of these, but I just did a quick Google search and was able to download this. All you have to do up here is type in your components, right? So my components here for the I is negative y. And then here, this one is x. Like that. And you have a couple different options here. You can zoom in and zoom out. You can change the density of the x there. You can change the density of arrows in the y sense by adjusting these. And all that's doing is just having GeoGebra plot more and more arrows on the screen. You can make you can change the length of the arrows, relatively speaking, the scaling. All right, and so you can say, that's not very helpful, but you can increase the length here so it makes a little more sense. And for some reason, you can also change the arrowhead, how tall or how big the arrowhead is. So there's some adjustments there. But here you get the sense that we get swirl, we get a rotation, don't we? You can also adjust the min and the max, all sorts of things here. And so, yeah, that is one way to do it. And you sort of get a sense of flow. How is stuff moving in this universe, right? And for instance, if I was a particle that was to drop into existence like right here, I would be wanting to move this way, right, to go with a flow. And as soon as I move to the left, well, I'm going to hit an arrow that says start to curl down this way, start to rotate, right? And so I'm going in circles, basically, right? And same with here. Now, if I'm going here, I'm going in circles quickly because the velocity vectors are much longer here, right? And so this is a nice way of sort of really figuring out flow in a situation. This could be air turbulence, this could be forces, this could be velocities, this could be accelerations, all sorts of applications possible here. In a math class, we're going to stick with the calculations and like what we can do with them, but keep in mind that, yeah, we can do many different types of applications here with this. Yeah. Okay, awesome. So graphing these are not going to be a big deal. You're going to be able to use technology to do that if you need to, or just plot a few on paper to get a sense of what's going on there, right? Let's get on to different types of vector fields. There's a good type that we want to work with, and I say good because it actually makes something really nice happen, and that's the idea of a conservative vector field. Conservative vector field. Okay. This is also going to bring in something with the gradient. If you remember, the gradient was the mathematical object that acted like a derivative, right? I take a function f of xy, and I calculated the gradient, and that gradient acted like a derivative in many ways. This was back in chapter 13, right? Well, now the idea of a conservative vector field is going the opposite direction. It's saying, if you have a certain vector field, did it come from an existing little f function? In other words, this is an idea of anti-differentiation. If going from f to del f equaling some vector field, if that's differentiation, then I want to start with a vector field and see if I can get back to little f. And that would be anti-differentiation. What we're going to say is that only those vector fields that we dub conservative will be able to go back this other direction. So it's kind of like functions in Calc 1. You could differentiate functions using rules, but sometimes you couldn't integrate them. You couldn't go back because they didn't have a closed form. I'm thinking specifically of, if I was in Calc 1, you could take the derivative of e to the x squared, right? That was no issue. To calculate the derivative of e to the x squared, you would say e to the stuff times the derivative of the stuff, right? But if I had to ask you the integral, the antiderivative of e to the x squared, this actually does not have a closed form integral. See that? So not all functions does there exist this antiderivative idea. Do you see that? We're going to see that not all vector fields come from little f functions, which we call the potential functions. In other words, not every vector field has an associated potential function that's its gradient. Okay? Now I'm getting ahead of myself. Let me define conservative vector field, and we will work with that idea. Okay? So the definition of a conservative vector field is the following. We say a vector field F is called conservative. And this is conservative in like the conservation of energy, right? That you may have heard of in physics class, right? The conservation of momentum, that idea of conservation, that's what we're talking about here. And it's very much tied to those physics applications. So if you're thinking, why is it a conservative vector field? Well, it's a vector field where something is conserved, and that something is usually represented by some physical thing, right? And so we have a conservation of that physical process. And so we borrow that name from physics, right? So a vector field F is called conservative when there exists a differentiable function little f such that the field vector f is equal to the gradient of little f. The function little f is called the potential function. For capital F. Okay. And potential function's no accident in naming as well. It has its connection with potential energy, right? And working with the conservation of energy, the kinetic energy and potential energy. There is no accident in that this wording is used because this shows up in that application. Okay. But for our purposes, in a pure like math sense, I have a vector. If I have a vector field, that I can find a little f function, take its gradient, and it matches that vector field. If I can do that, then we call that vector field conservative. And then we call little f the potential function, and we call capital F the gradient function, right? Because it's the gradient of little f. Yeah. Okay, so let's take a look here at some examples. Our first example is the following. Let's determine, is f of xy equaling 2xi plus yj conservative? Okay. Now, I'm going to do some secret work to show you. We'll learn how to find this in a future class either. Well, I think in a little bit, actually. I think that they show you how to do that in this section. Regardless, let's just say I'm going to be almost magical here. Consider little f of xy equaling x squared plus 1/2 y squared. Okay? I just created that out of thin air. No, there's going to be a process, which we can find it, and I'll show you that in a little bit. But for now, let's just say, look at this. I found little f, and it's x squared plus 1/2 y squared. Right? Check. Calculate the gradient of little f. Well, what's the gradient of little f? I'm going to take the derivative of this with respect to x, which is 2x. That's the I component. And then I add to that, take the derivative of this with respect to y. That's going to be y, and that's the j component. But wait a minute, that's capital F. So in other words, this function, this field, is conservative. So the answer is yes, f is conservative. And little f is the potential function, or the potential, if you want to call it that. See that? Now, again, you might be asking, how did you find that? We're going to do that in a little bit. But to make sure to just check conservative, all I need to show is there exists a function. And I did that. Doesn't matter how I've conjured it up, right? I've shown that a function exists where I take its gradient, I get that function, that field, and so it's conservative. All right? Any questions with that? Any questions with that? Okay. Okay. So this might be difficult to actually find, right? Because it is an existence theorem. And so you have to go out and like seek it out. You have to like, go find it. Go find little f. Now that may be easy and it may be difficult, right? There's a handy little test for conservative. And so this is much easier than finding little f. But of course, it doesn't find the potential, but it at least tells you if your field is conservative or not. It won't tell you what little f is, but it'll at least confirm whether it's conservative or not, whether one exists or not, right? And so we have a test for conservative field. Okay. We're going to say f of xy equaling some m function I plus some n function j is conservative if and only if. Okay. We call that a characterization in mathematics. That means that this completely characterizes the next thing I'm going to write, which means that whenever you see this, you get this, and whenever you get this, you get that, right? Works both ways. And here's the little calculation that you can do. The partial of n with respect to x equals the partial of m with respect to y. Okay? And that is a lot quicker to calculate. So if you only need to know is the field conservative or not, this will answer the question. It doesn't answer the question of the little f because by definition, a field being conservative means there exists a little f. So this won't find little f, but it'll at least guarantee one exists or doesn't exist, if this is true. Okay, so let's go ahead. What I could do now is do a couple examples here. And we now have a nice new way of determining whether functions, fields are conservative or not. And so let's ask the question to this field. Is this a conservative vector field? X squared yi plus xyj. Okay. Now all you have to do is think of this first function here as m. Think of this as n. You're going to look at n and take its derivative with respect to x. And you're going to look at m and take its derivative with respect to y. Do you see how there's kind of like a cross product thing going on? Right? It's like take n with x, take m with y, right? So let's go ahead and do that. I'm going to calculate the partial derivative of n with respect to x. That means I'm looking here and taking the derivative with respect to x. That's going to be y. The partial of m with respect to y, that means I'm looking here and taking the derivative with respect to y, which should be x squared. Okay? And you can see that these two partials, not equal. Not equal. So therefore, f not conservative. Yeah? F is not conservative in this case. Yeah? Now that might represent something in physics, a non-conservative force, right? Something like friction, right? Friction is not a conservative force, yeah? And so that would represent some different force like that. In general, though, in mathematics, what we're saying is there's no potential function that exists here, right? For this field, yeah? Okay, let's try another example. Let's check this. 2xi plus yj. Oh, I think we proved this was conservative because I magically conjured up the potential function. But now we can do this test to say, hey, guess what? This is more likely what we're going to be able to do, right? We're going to test it first. It's going to confirm that it's conservative. Then I go out and try to find little f. Do you see that? But it's nice to know that it's conservative first, so then you know there's something to look for, right? All right. So here again, I'll take the partial of n with respect to x. So I'm looking here. That's going to be 0, because y is a constant relative to x. Take a look at m with respect to y. I'm looking here, derivative with respect to y. That's also 0. These are equal, so f is conservative. And what does that mean by definition? Therefore, there exists a function f, little f, such that, take the gradient of little f, that's going to be this function field here that I have. Right? And maybe up here I should say, therefore, there does not exist. A function f such that the gradient del f is equal to capital F, like that. Right, so do you see that this is the idea of, this has an analog in Calc 1, right, where it's saying, okay, great, there does exist a function that when I take its derivative, I get this. That means there exists this antiderivative. For this case, there does not exist that antiderivative idea. See that? And so if I was doing the fundamental theorem of calculus in Calc 1, this would be awesome because there exists an antiderivative. And so the fundamental theorem is easy, because the fundamental theorem says if you have an antiderivative, then that definite integral is just the difference, right? Plug in the b, subtract, plug in the a. Here, though, I would be stuck. I would not have the benefit of a fundamental theorem because I do not have the benefit of an antiderivative here. See that? So there's certain fields that work very nicely mathematically, and there's others that are not so nice. We group these all together as into conservative and non-conservative. Okay, awesome. Let's get into the problem of finding little f if it exists, right? Unless there's any questions before I move on. Okay. Finding a potential function for conservative f of xy. Okay. So this is going to be a technique to find little f. And to find little f, it might not surprise you that it's going to require integration, right? Anti-differentiation. In other words, to find the little f whose gradient is capital F, I am going to need some anti-differentiation to find that. All right, let's walk through this example together. Find a potential function f for capital F of xy, which is 2xyi plus x squared minus yj. Let's first guarantee that one exists. So first, confirm that f is conservative. There's no point in finding little f if it doesn't exist, right? And so let's confirm that capital F here is conservative, okay? So again, think of this as m, think of this as n, okay? And now I'm going to say what's partial of n with respect to x. So I'm looking here. and taking the derivative of this with respect to x, which is 2x. Then I'm taking the partial of m with respect to y. So I'm looking here, taking the derivative with respect to y. That's going to also be 2x. There we go. That's confirmed. Those are equal. Okay? Those are equal functions. Can you all hear my TA? Your TA is barking her head off. I don't know what she's barking at. She's excited about conservative vector fields. I know I am. Okay. So let's start this process. I want to now construct little f. I want to construct a function that when I take its gradient, I get capital F. Okay? So here's what I start. Start with the following. We don't know little f, but we do know that this component has to be the partial of f with respect to x. Right? That's by definition of a gradient, right? The gradient says this has to be fx, this has to be fy. So start with that given knowledge. We're going to assume that little fx is 2xy and fy is x squared minus y. That's what it would mean for this to be a gradient, right? Is that the partial of f would have to be this, and the partial of f with respect to y would have to be that. So we start with that and that. Okay? Now, what we can do is take the integral of this. Let's do a partial integral. It should be true that f equals the integral of fx dx, right? Which gets me the antiderivative of 2xy dx. Now, what I'm going to be able to do here is recover a piece of little f. I'm not going to be able to get the whole thing because I'm only using a partial, right? And so let's see what I end up getting here. Remember how to handle this. This is partial integration. So that means you treat the 2 and the y as constant and x is the variable. So what I can do here is x, the 2y goes out in front, x squared over 2. So I get x squared over 2. The 2's will cancel, and the y stays there. Now I get a plus constant, but remember, since I'm only integrating with respect to x, this is not just going to be a plus c. This could be literally any function of y. So let's call that g of y. Right? Let's call that g of y. And notice this makes sense if you go backwards and take the derivative of this with respect to x. You're going to get 2xy, and then you're going to take the derivative of this. I don't know what that is, but if it's only a function of y, taking its derivative with respect to x gets me 0. So what I know so far from halfway into this process is that little f must have x squared y in it, and the rest is just function of y. I now need to find out this unknown function. Once I find this unknown function, then I'll know the complete story for f. Okay? Everyone with me so far? So I have a piece of little f. Now my next goal is to come up with this unknown g of y. Okay. Now how am I going to do that? Well, I haven't used this information yet. I haven't used my other partial, right? So what I want to do is take this partial that was given, and then I want to calculate that partial according to what I have and reconcile the two, right? I have a candidate for little f. Little f looks like this. So when I take its partial with respect to y, it better match that. Right? So here's what I'm going to do. I'm going to take this and I'm going to calculate fy from my little f that I calculated here. So take the derivative of this with respect to y. I'm going to get x squared plus, now this is a single variable function, and I'm taking its derivative with respect to y. Let's call that what it is. Isn't that just g prime? This is back in Calc 1. What's the derivative of g of y with respect to y? G prime of y. Right? I can at least say that. I don't know the specifics, but I do know that whatever this is going to be g prime. That's what I've calculated fy to be. Now set that equal to what fy is, which is x squared minus y. See that? And now I have an equation. If you've done this correctly, at this point, all of the x stuff should cancel out. Why is that? Because this says I have to have a function of only y. So there can be no x's left. Right? And notice what happens if I subtract x squared from both sides. I end up with the equation g prime of y equals negative y. Do you see that? The x squareds drop out. I do get a function that's just of y, no x's. That's a good sign that you're doing it right. If you had jumped into this problem and you didn't confirm it was conservative, you'd start to get contradictions here. You'd get an x and a y values that just wouldn't go away, and then you would say that it would have to be a pure function of y. And that's a contradiction, meaning that you probably missed the fact that maybe it's not conservative and maybe a little f does not exist. It would break down right here if you tried to do that, right? But don't let it get down to this far. Test them first, yeah? Make sure you've proven that it's conservative first, then you won't reach problems here. Okay, so now let's recap where we're at. I don't know g of y, but I do know its derivative. So how can I find g? Well, g should now be the antiderivative of g prime, which in other words, I'm going to take the integral of negative y dy. This is going to be negative y squared over 2, right? Plus any constant you like, so plus c. And this is a plus c because this is single variable. We're back in Calc 1 in this by now, right? But there we go. We have a description for what g is. That means I know what this is, which means I now have a complete story for little f. Let's recap and write what I got. What I'm going to say here is that little f is this function. It's x squared y plus a minus 1/2 y squared plus c. That's my potential function. How can I check? Well, if I take the partial with respect to x, I should get the first component of my field. In other words, if I take the derivative of this, I get 2xy with respect to x. That's gone, that's gone. See that? 2xy, I. Nice. If I take the derivative of this with respect to y, I'll get x squared minus y. X squared minus y is the j component. There it is. I found that function. Plus c, any number will do. And so, yeah, this is my potential function. Usually we ignore the plus c, but any constant plus c will work as a potential function. So there are an infinite number of potential functions if one exists. All right. Any questions on that? How are we doing with that? Take a second to reflect onto that, on that method. Okay. Yep. In chat, I like this more than chapter 14. Some students do. They say they like this better than the integration. And personally, I agree. I kind of agree with that. Okay. All right. It is easy to sort of confuse the two concepts of, potential function and field, vector field. So continually say that to yourself, right? Be very, very specific when you work with this, right? It's like, okay, I have a vector field. The vector field is conservative. That means there exists a little f called a potential, such that when I take its gradient, I get capital F. It's good to sort of say that out loud a couple times to really get the players involved here. to get your vocab going in the right direction there, yeah? Okay, awesome. Our next idea that we're going to talk about is how does a vector field change? How does it change, right? So if you think about, think about liquid swirling around, right? And, under some influence of whatever, right? And you see that flow. You see the water flowing and it either rotates or it just moves side to side, right? You can think of multiple applications where you have a vector field and you want to ask, how are things changing in this vector field, okay? What I'm going to do here is, give me a second here, I'm going to upload, I'm going to actually show pictures from the old textbook, because again, I like the description and the pictures it uses, and our book just doesn't have that. So let me get this ready. Because now it's time to talk about the derivative of a vector field. What does that mean, right? What could that mean? Well, one issue that we have is there's actually two different ways a vector can change, right? Let's think about this just before I get into details here, right? Obviously, a vector, one source of change would be that it goes from this to this long. So I could say that this has changed because what? Its magnitude has changed, right? So that's one aspect of how vectors can change. They can change magnitude, right? But on the other hand, I would say this vector has changed into this vector. Same magnitude, but they've changed direction, right? And so when I say, how do I measure the change of a vector field? It has to have some aspect of the magnitude changing, because that's one aspect of how vectors can change. And it also has to have the aspect of changing direction, right? Maybe a rotation. Maybe it went from, this way to this way, right? And so there's going to be two concepts of derivatives. These two concepts have weird sounding names at the beginning, but they do actually make some sense once you work with them a little bit. But one derivative, if you will, of a vector field is called a curl. C-U-R-L, a curl. Let me write it under here because this one represents curl. And the other one, the other type of derivative thing that we can calculate is called divergence. This is not the divergence of series in Calc 2. So if you remember that, you might say, oh, this series is divergent, or it diverges, or we have divergence. It's not the same concept, right? And so this is divergence as in the divergence of a field, okay, or the curl of a vector field, all right? Let's go ahead and look at some pictures. I want to introduce the idea first of curl, okay? So take a look at this, what we have here, okay? This really is a nice way of thinking about this. Thinking about, you have a vector field, okay? So you have a field of arrows. And let's say that, I've graphed it on GeoGebra. I can see the flow happening, right? Sort of get the idea of the sense of flow in this vector field. Now I'd like you to insert at some point that you're interested in a paddle wheel, right? A paddle wheel that's allowed to spin, right? That's allowed to spin like this. And now consider a vector field that looks like this. Let me zoom in here, like that, okay? Now this is the vector field yi. Now this is a three-dimensional, they're saying it's a three-dimensional vector field, but we're only seeing the I component of it. Three-dimensional vector fields work the same as two, it's just extra component, right? I, j, or k is available. So I'd like you to think about visually, go here with me. Things on this line are slow. Things on this line are a little faster, if you're thinking about this as velocities or even forces, right? On this line, they're even faster. or stronger, however, whatever adjective you want to describe this with, right? And then this, they're really strong, and 5 is really strong. It seems like as I move vertically in this world, I have more force or more velocity acting on me, right? Would you agree with that assessment here? Just looking at this picture, right? So this is slow to fast as you move up. Now imagine if you inserted a paddle wheel here at some location. You just plopped it in right there, okay? The question I have for you is, would that cause rotation? Would the paddle wheel start to rotate? And in what direction or what orientation would a paddle wheel start to spin? Just what does your intuition say? Right? Would it go clockwise? Would it go counterclockwise? Or would it not spin at all? Right? Now, again, remember what these arrows represent. These arrows represent like force. So there's more force acting on the top than there is on the bottom. More force on the top than the bottom. I think there's a picture over here to sort of really zoom in on this. Yeah, do you see this? So as I go higher up in Y value, right, I end up having more force on that paddle wheel. And the force at the top is more than the force on the bottom. This is going to induce, as Christian said in the chat, yeah, very good, a clockwise rotation. Right? Would you agree with that? So it says flow through a neighborhood of P at which a paddle wheel is located. This is going to have clockwise rotation. Okay? So let's remember that. This field here, the field YI, seems to invoke a clockwise rotation. So I'm going to jot that down, and then I'm going to show you a couple more pictures here. Okay. This next field is the one that we were working with earlier, negative yi plus xj. And let's go ahead and look at their graph. Sorry for the big words there, but yeah, here is their version of this spin field, this vector field here, right? And go ahead and plop down your paddle wheel. Now remember the trick to this one, right? As I moved further from the center, the velocity or force got larger, right? These were magnitude 1, if you remember from earlier. Things on this circle were magnitude 2, and things here were magnitude 3. So the further away you are from the origin, the more force or velocity you're experiencing. Okay? You're a paddle wheel, plopped right here at this location. Does this induce a rotation of some sort? Will your paddle wheel rotate? And if so, what direction, what orientation? Right? To help us look, let's zoom in. So this is a zoomed in picture of the paddle wheel. And you can see that since this is really close to the origin, right, this has a certain magnitude. But I do know that on the opposite end, this is going to be larger magnitude because it's further away from the origin, right? Same with this, right? If I'm here and then I look over here, this is further away. So this is more magnitude over on this side of things than it is on this side of things. So now, what do you think? Does this induce a rotation? I would certainly think so, right? There's more force acting this way. This is going to be a counterclockwise rotation. Or for our UK friends, anti-clockwise, right? Some folks say anti-clockwise. Some say counterclockwise. But does that make sense, right? There's going to be a little bit more force. So there's going to be a twisting that happens, or a rotation that's going to want to happen, right? Now, of course, this whole thing could be moving, right? It could be translating, but it's also rotating as it moves, right? Yeah, so I'm not talking about the translational. I'm not talking about that sort of change. I'm purely focusing right now on, is it rotating clockwise or counterclockwise? And so here I'm going to jot down that we got counterclockwise rotation here. Okay. All right. Next example. Xi plus yj. Okay. Here's a picture of that field. Now, the field xi plus yj has arrows that have more magnitude radially the further out from the origin you are. But every vector on this circle has the same magnitude. But that magnitude increases as you make larger and larger circles. Okay. So now imagine flow starting off slow and then picking up force or speed. And it hits this paddle wheel. It hits that paddle wheel, right? Does it rotate? What's your opinion on that? Does this cause rotation? Well, this enters like this, and it has a certain magnitude, and it exits stronger, more magnitude, because it's further away. So you might think it goes clockwise, except there's the very same thing happening, equal but opposite, on the other side. This is trying to pull this way, and even stronger pull once it exits this way. So you might think it wants to go that way. Do you see there's a balancing out here? This paddle wheel will be stuck. It is not going to rotate, right? Because the flow is such that it's just radiating out and it's not causing a rotation. There's not like a force on one side causing it to rotate, right? So I would say that this is zero rotation. Okay. How are we doing with that? Are we okay with those three pictures? Does anybody want to see those again, or are we okay? Thumbs up in chat if we're okay. You're good, okay. Thumbs up, awesome. Okay, now, what I've just described to you is the physical intuition of what we call the curl of a vector field. The curl measures, in essence, the amount of rotational change a vector field has. You tell me a location, you tell me XY, that was me putting in the paddle wheel at a certain location, and I will calculate the curl of the field to measure the type of rotation that we have. It's going to tell me if I have clockwise or counterclockwise rotation. It's going to tell me how much rotation that I have, right? And so let's get to our definition. What tool does that? And believe it or not, there's a calculation for this. Now, the calculation, though, does look a little scary, okay? And so I'm going to write this out, but there's going to be a way that we handle this that's not nearly as scary as the definition looks, okay? So definition of curl. Of F, a vector field, okay? By the way, this is a 3D concept. Curl only makes sense in a 3D concept. Now, why did I show you two-dimensional pictures and flow? At all cases, do you notice that the rotation was on a vector perpendicular to the paper, right? So again, if you've had some physics, this is very much like angular velocity, right? Or angular momentum or angular acceleration, right? Where you have rotation about a certain vector, right? And so all of that rotation that we had was acting about a vector orthogonal to the plane. Right? That's how we think about rotation. Right? You can think of it a pole at the origin, and things are rotating around it. Right? So rotation requires like a point at a location that we can work with. Yeah. Okay. Awesome. So here we go. The curl of F is a vector. So the curl of a vector field is a vector. So if I have mi plus nj plus pk, okay, we have a couple notations for the curl. You can just say curl F. That's one way to denote this. A fancier way, and again, if you've had some advanced physics, you might recognize this as something that's in Maxwell equations, del cross F. This is del cross F, otherwise known as the curl of F. Okay. Now, why is it written like that? Because it does involve a cross product of in a certain way. Okay. Here again is the scary way of writing it out. Partial of p with respect to y minus partial n with respect to z. That's the I component. Built-in minus partial of p with respect to x minus partial of m with respect to z, j. Plus partial of n with respect to x minus partial of m with respect to y, k. No one memorizes it this way, right? So I do want you to think about this cross product, because this will allow us to calculate curls decently well without having to memorize this just jumble of notation and letters, right? So let me finish out this definition, then we'll do the example. Find the curl of the three examples we had earlier, right? Okay, so if the curl of F is the zero vector, then F is called irrotational. Irrotational. So in some sense, there's no rotation change in that field. Okay. Like I said, this looks scary, but I promise you it's not bad. Okay. Let's go ahead and demonstrate what this means. What does del cross F mean? Here's what I mean. Think of it this way. The top row is I, J, K. Del is the partial operator, right? Which means literally just take the derivative with respect to x, take the derivative with respect to y, take the derivative with respect to z. So this is an operational thing. It's saying, giving you an instruction, right? Then the components of F are M, N, P. Okay. If you think about it like this and do the cross product, our standard cross product, you will end up writing that. Okay. But this is the way you think about it when you actually calculate curls. Okay. Let's go ahead and do an example. The first example I had was clockwise rotation for yi. Okay. So let's go ahead and do that. Okay. So, example, let's say that the function xyz is yi. Okay. Let's calculate the curl. The curl of F equals del cross F. And I'm going to set that up by saying I, J, K, partial of x, partial of y, partial of z. And here, I'm going to have y in the I column, a 0 here, and a 0 there. Okay. Now I go ahead and take that cross product. And when I do this times this, when I say this times this, times with an operator just means perform that operation. All right, so when I go ahead and do this, I say, okay, I You cover up this row, you cover up, sorry, this column and this row. And what you're going to say here is that take the partial with respect to y of 0. Well, that's 0. Minus take the partial with respect to z of 0. So I get 0 minus 0. So I is 0. Okay. Then remember in your cross product, negative is built in. J. Now hide the j column. And we're going to say, take the derivative with respect to x of 0. Well, the derivative of 0 is 0. Minus, take the derivative with respect to z of y. But that's also 0 because y is a constant relative to z. So the j component is 0. Okay. Plus k. And how do we get the k? Let's see what we got here. Hide the column of k. Take the partial with respect to x of 0, still 0, minus the partial with respect to y of y. What's the derivative of y with respect to y? 1. And so I have calculated the curl vector of this field. Okay? So if you wanted to, you could think of that. Remember how we had that two-dimensional picture? The curl vector was pointing straight out from the screen at you. It was the k vector pointing straight out. So this would be the flat screen. Would it be -1? Did I mess up? It is. Yep, it is. Thank you for that correction. Yeah, because it's the -1 of this. That's right. So it's this minus that, and I forgot my minus. Thank you so much for pointing that out. This is going to be negative k. Okay. Awesome. Notice, and that's super important. I'm glad you caught that because negative k, that negative, right? Notice that the rotation was clockwise, right? Remember in trig class, when you had rotation this way, if you went counterclockwise, we called that a positive rotation. And in trig class, if we went this way, right? If we went clockwise, that was actually a negative rotation. And you're seeing that here. Do you see this negative is confirming that I have the clockwise rotation? See that? So think of this as the vector that the spinning, the rotation is happening around. And the negative gives me the orientation that it's going around clockwise. Okay. Awesome. Let's go ahead and do the other ones real quick. We could find the curl of the middle one, which was f equals negative yi plus xj. This is the spin field. We noted it had counterclockwise rotation. Okay. Let's go ahead and calculate the curl of that. And I'll try not to screw this one up. ijk, partial of x, partial of y, partial of z, negative y, x, 0. Okay. Doing the I, that's going to be 0 minus 0. J, 0 minus a minus 0. Plus k. K is going to be, what is that? 1 minus, let's see, wait. Partial of x with respect to x is 1. Minus a minus 1. So I got 2k. Okay, see that? 2k. So I can tell that rotation is happening orthogonally in the plane orthogonal to 2k. Notice that it's a positive orientation. That gives me the counterclockwise. And the rotation is faster than the previous one because the magnitude of this is 2. And the previous one was magnitude of 1. So this is in some sense, saying that it's rotating counterclockwise and at a constant 2, right? And it's a measure of its angular velocity in a sense. Yeah. Okay. For our last one, this one we got was irrotational, right? We got 0 rotation out of it. Let's see if the curl confirms. This one was 0 rotation. I calculate the curl. Let's see, x, y, 0. Going ahead and do that quick. We got 0 minus 0 minus j, 0 minus 0 plus k. Partial of x with respect to, y with respect to x is 0 minus, 0, 0. And so there you have it. This field is irrotational. Okay? So that's how we can handle measuring the rotation of the field, right? If there's any rotation, if it's changing in that aspect, yeah? Let's comment quickly on the second way of changing or how a vector field can change, and that's its divergence. Okay, that's its divergence. So curl measures rotational changes. What does divergence calculate, right? Let's go back to some pictures here. Okay. Let me off screen so I can scroll to where I want. Okay. So here we go. Here's a picture. So this first vector field that we're going to talk about is xi plus yi. So we already talked about that vector field. We talked about its curl anyway. Okay. But now I want us to look at a different sort of measure or flow that's going on here. P is no longer, this is not a paddle boat or paddle wheel, right? Now you're just thinking about what sort of flow is going in and what sort of flow is going out. Is there more flow going in and then less flow, or is there going from less to more? Or does it stay roughly the same? So you go ahead and take a look at this picture here, and you think about, well, what enters this neighborhood? That's where the capital N comes from. They're like, okay, here's a little neighborhood in the vector field. Think about, how does flow work? Well, remember, this one has the further away you are from the origin, the stronger the flow, the stronger the velocity, the stronger the acceleration, field, force, whatever, right? Let's zoom in. Okay. So take a look here. Sorry. So take a look at this and notice that we have flow going in at a certain magnitude, and this is closer to the origin. And this is going to push through and come out the other side, but it's going to now be affected by more magnitude. How do I know that? Because in this vector field, when you're further away from the origin, you have more magnitude. Right? And so you can see these small magnitude things going in, but they exit with more magnitude, right? So it picked up strength, if you will, right? It went in a slow flow, and then it sort of sped up as it exits the neighborhood, yeah? So let's take a look at that. That meant that we have, and I always want to make sure I get this right, we call that a positive divergence, right? More fluid leaves than enters a neighborhood of P, right? So this, we're saying that more fluid leaves the neighborhood than enters. And so we say that that's a positive divergence. I'm going to go ahead and jot that down. Positive divergence. Okay. For the next one, this is yi. Okay. Take a look at this, and again, I'm not asking about the paddle wheel. I'm not asking about rotation. I'm asking about the flow in and the flow out, right? So now take a look here at the flow that goes in and the flow that goes out. Remember, this is the vector field where the higher your y coordinate is, the stronger it is, but it's traveling horizontal, so you're staying the same magnitude as you travel horizontally, right? So think about what goes in and what goes out. There's a certain flow that goes in, but since it's perfectly horizontal, the exact same flow goes out. Even though this is slow flow here, it's the same amount of slow flow that goes out. Do you see that? And so I would say that this is 0. The same amount goes in as the same amount goes out. Would you agree with that? We would call that 0 divergence. Right? It's a net neutral. Right? Okay. Then for our third example, we have 1 over x plus 1I. Okay, we haven't worked with this field before, so let's take a look at how these arrows work. See this? This is, as you move horizontally, it goes real fast at first and then slows down the further you are away. See that? Like that? Right? And it looks like it's the same behavior no matter what your y coordinate is. Right? So let's think about the flow going in and the flow going out of a neighborhood. So take a look here. A flow is going to go in, but because this is further to the right, and I know in this field as I go further to the right, the flow is reduced, the magnitude is reduced, there's more coming in than going out. There's more coming in than going out. That is called a negative divergence. More flow out, more flow in than out. That's a negative divergence. Okay, now that you have sort of a visual of what divergence is and what it's measuring, the calculation to find divergence is actually really easy. It's not bad at all. So let's go here and we'll define that. We'll do our examples, and then we'll call this a video, and we will get on to Thanksgiving break. Yeah? So let's do this. Definition of divergence. Of a vector field. Okay. So if f of xy equals mi plus nj, you can have the divergence, by the way, of a 2-dimensional or a 3 or a 4 or a 5. And so like any number of components, this would scale up. Right? Let me go ahead and write the 3-dimensional version down. So if the field is this, we will say that the divergence, which is div f, the divergence of the field, here's the notation for that. It's del dot f. Remember how curl was associated with cross product? It looks like divergence is associated with dot product. That means that the divergence is going to be a scalar function and not a vector. So the curl of a vector field is a vector, and the divergence of a vector field is a scalar, because one's associated with cross product and the other's associated with dot product. Nice. The definition is as follows. All this means is you dot these together. So you take the derivative with respect to x of the first thing. So that's going to be del m, partial of m with respect to x, plus take the derivative of the middle one with respect to y, so plus del n, partial y, plus partial p with respect to z. And if it was only 2, you wouldn't have this third part. It would just be that. Yeah. If the divergence of a field is equal to 0, and I mean scalar 0, the quantity 0, because it's not a vector, it's a scalar, it's said to be, F is said to be divergence free. Divergence free. Okay. All right, let's go ahead and calculate the divergence of these 3 examples that we just did. Okay. So for example, let's see, let me remind ourselves of this. We had xi plus yi. Xi plus yj, I mean, right? Yep. I said xi plus yi, and I actually wrote that. I think I mean yj. Yeah. Okay. Let's do the divergence. What's the divergence of this? Not bad. Del dot f is going to be, take the derivative of this with respect to x. That's going to be 1. Plus, take the derivative of this with respect to y, which is 1. So I get a divergence of this field is 2. That's a measure of its flow. It's positive, right? So that's positive divergence. And that meant what? That more, shoot, I lost my picture. Positive divergence meant what? Like more goes out than in, right? More goes out than in. I think I said that right, yeah? Okay, the next one was negative, sorry about flipping it all the time, yi. So the divergence, thanks, Christian, yeah. Divergence of f. Okay, check this out. Be careful here. This is the I component, right? So you take the derivative with respect to x. What's the derivative of y with respect to x? 0. So that middle one was divergence free. The same amount of flow went in as out. There was 0 divergence. And then finally, that last one was 1 over x plus 1 I. Okay. Let's calculate the divergence of that field. That means I need to take the derivative of this with respect to x. Okay. So yeah, let's think of that as x plus 1 to the negative 1. So I'm going to have negative x plus 1 to the negative 2 times the derivative of the inside, which is just 1. And that's I. Oops, not I. Not I. Divergence is a scalar. Divergence is a scalar. And then no other terms, right? 0 terms. So what do I have? I have negative 1 over x plus 1 squared. Now, here's something interesting, right? Notice that the divergence of this field depends on your x value. Do you see that? So the larger your x value, the less negative the divergence. Said another way, as this gets closer and closer to 0, as x gets closer and closer to negative 1 here, this denominator gets really large, right? So as I get closer and closer to that, I get more and more negative divergence. So this divergence is not constant. The divergence is a function of x, of the x value. But with that being said, notice that at all times, it's always negative because it's 1 divided by something positive, something squared, then the negative of that. So I can tell that this is going to be a negative divergence. See that? So that's your quick sort of introduction to vector fields, right? We have a little bit more work to do with this, but we are pretty much done with 15.1. What could we go into next? You might imagine, like, what is there to do next? Well, if you can believe it, there's a type of integration that we have not talked about yet. You're like, no, I thought we were done with integration. Well, we have one more thing to talk about integration, something called a line integral. And frankly, the line integral is a terrible name for it because it should really be called a curve integral. And so we're going to have to talk about that next week once we get back. A different type of integration. It's going to tie into physics if you're interested in that. It's going to tie into calculating the work done by a field, which is a very important calculation that's often done in physics as well. All right, everyone, I hope you're doing really well. I hope you have a great break. Hope you find some time to rest and to recharge as best you can. But I know it's busy, and so take care of yourself any way that you can. Yeah, wishing you good health and looking forward to checking in with you on Tuesday, 1 week from tonight. Hope you have a great Thanksgiving if you celebrate, and looking forward to next time. All right, until then, be well. Bye now.